Welcome to the deep dive. We're jumping straight in today with a really core idea in statistics, maximum likelihood estimation, MLE for short.
Yep, MLE. And we've got some great material here that, well, it really unpacks this fundamental principle.
So the mission for this deep dive.
Basically, understand why MLE is such a big deal for analyzing data. We want to pull out the essentials, what it is, how it works, why you should care.
Okay. Without getting totally lost in the formula.
Exactly. We'll touch on the basics, like the core idea, maybe how it works for simple cases like coin flips.
Like the Bernoulli stuff.
Yeah, and optimization, log likelihood, maybe how it compares to other methods.
All right, let's do it. So foundation first. What's the absolute core principle behind MLE?
Simply put, MLE says find the rules, the parameters that make the data you actually saw the most probable thing that could have happened.
Okay, so you look at your data and you ask what parameters would make the specific data most likely.
Precisely. It's about maximizing that likelihood.
Makes intuitive sense. So, how about that simple case you mentioned? Flipping a coin, the Bernoulli distribution.
Right. Say you flip a coin 10 times, get 7 heads. Bernoulli models the probability of heads. Let's call it P.
Okay.
The likelihood function then calculates how likely that specific outcome, 7 heads, 3 tails, is for any possible value of P.
Hmm.
MLE's job is then to find the one value of P that gives that sequence the absolute highest probability.
So it would probably land somewhere around 0.7 in that case.
You got it.
Yeah.
It finds the parameter value that best explains what you observed.
Okay. Now, you mentioned optimization. How does that come into play? Finding that peak P.
Exactly.
Yeah.
Once you've written down that likelihood function, actually finding the exact value of P that maximizes it often needs, well, some computational help.
Like algorithms.
Yeah, optimization algorithms. Think of it like climbing a hill to find the highest point. The algorithm does the climbing.
Yeah.
And often we actually climb the log likelihood hill instead.
The log likelihood?
Maybe
Why the logarithm? Does it change where the peak is?
Good question. No, the peak stays in the same place. But taking the log often makes the math way simpler.
How so?
Well, logs turn multiplications, which can get messy with lots of data points, into simple additions. Much easier for computers, especially with tiny probabilities.
Ah, okay. Easier number crunching. Now, there's another method people often hear about, least squares. How's MLE different from that?
Right, least squares. That's more about minimizing the difference, the errors, between your model's predictions and the actual data points. Like drawing a line as close as possible to a scatter plot.
Okay, minimizing distance.
Yeah. MLE, though, is focused on maximizing the probability of seeing the data, given a specific probability distribution model. It's less about geometric distance and more about probabilistic fit.
Different philosophies, really.
Kind of, yeah, based on different underlying assumptions about the data.
Our notes also bring up consistency. What's that about for MLE?
Consistency is a really nice property. It basically means under the right conditions as you get more and more data.
Mm-hmm.
Your MLE estimate will get closer and closer to the true value of the parameter you're estimating.
So more data generally means better, more reliable MLE estimates.
Generally, yes. Assuming your model isn't totally wrong, of course.
Right. The model assumption again. Okay, what about Fisher information? Sounds important.
It is. Fisher information measures how much information your data actually provides about the parameter you're trying to estimate.
So more information is better.
Definitely. High Fisher information means the likelihood function has a really sharp peak near the true value. Meaning your estimate is more precise, there's less uncertainty. In fact, the inverse of the Fisher information is related to the variance, the spread, of your estimate. More info, less variance.
Got it. And the Hessian matrix, that sounds a bit intense.
Yeah. Think of that likelihood landscape again. Hills and valleys. The Hessian matrix describes a curvature to
It's in the
peak.
shape of the hilltop.
Exactly. Is it a sharp spike or a flat plateau? A sharp spike means high certainty, low variance related back to that Fisher information. Optimization algorithms use the Hessian too to navigate and check they found a real maximal.
Okay, helps find the peak and know how confident we should be. But what if our initial model, the one we base the likelihood on, is just wrong?
Yeah. Model misspecification. That's the big caveat. MLE will still find the best parameters within the confines of your wrong model.
So the math works, but the answer might not mean much in reality.
Precisely. The parameters might be meaningless if the assumed process doesn't match the real-world process generating the data. Garbage in, garbage out, potentially.
A crucial reminder. Okay, let's make it concrete. Logistic regression. How does MLE fit in there?
Logistic regression models the probability of a yes-no outcome. Right. based on
Okay.
predictors.
Yeah, like predicting if a customer will click an ad or not.
Exactly. To do that, you need coefficients telling you how each predictor influences that probability. MLE is how you estimate those coefficients. You build a likelihood function based on the actual outcomes. Click, didn't click. And the predictor values for everyone in your data. Then, MLE finds the coefficient values that make the observed pattern of clicks and non-clicks the most probable.
So MLE is the engine finding the best fitting coefficients for that probability model.
It's the core estimation method used there, yes.
Okay, wrapping up then, key takeaways on MLE.
Number one, it's about finding parameters that make your observed data most likely, given a model. Two, it's used everywhere. Bernoulli, logistic regression, tons of others.
And things like consistency and Fisher information tell us about reliability and precision.
Right, under the right conditions. Consistency means it gets better with more data. Fisher info relates to the estimate's uncertainty.
Perfect. So final thought for our listeners. MLE relies heavily on that chosen model, even if the math checks out. What's the big thing to stay critical about?
Always question that initial model assumption. Is this probability distribution, this structure you've assumed, actually a reasonable representation of reality? Because even the best MLE estimate is only as good as the model it's based on. Think, could another model fit better? Are my assumptions justified?